Welcome to this presentation on the Introduction to Engineering Terminology in the Otto cycle. Again, there's a handout associated with this, so if you go to the link, the description below, you should find a link to that handout, and so you can follow along with that, or just follow along with the presentation and go to the handout later. All right, so let's get into it here. Where are we at in the forest of learning for applications of thermodynamics? And so we're looking at the Otto cycle today here with gas power systems. And we'll look at diesel and dual cycle next time. Actually, this one's going to consist of two different presentations on the Otto cycle. All right, so motivation, maybe this image is enough for you. Maybe thermodynamics in general is enough for you. But what we're looking at is the Otto cycle, which has to do with looking at how engines work, specifically the piston cylinder creating energy, power, from the combustion process. So what I want to start with today is an animation to help you have a better understanding of what we're dealing with here. So let me go over to this website and slow it down a little bit here. And we'll come back here. All right, so what we have here is what I want you to focus on is the piston, and obviously we have the overall cylinder here. What we have is two valves, and this one is letting in our gas-air mixture. So it's a mixture of the fuel that you would have put in the tank of your car and air from just the outside. And so that's already been pre-mixed, and so this valve is letting it in, and as the cylinder moves down, it draws it in. It draws in that mixture and then pushes it back up. Now the valve is closed, so now the pressure is increasing, and it's pushing it back up till near the top when the spark, right there, a little red dot, spark goes off to ignite the mixture, creating this ignition, and it starts burning, and that drives the piston downward, creating energy down here in the crankshaft and ultimately turning the wheels. Right, and then that keeps going down. So I'm going to slide this all the way back because that's just how they did the animation. All right, so now it's pretty much been all burnt. And what we're going to do is exhaust it. We're going to let it come out. And so if I move this forward, the exhaust, this valve opens, and all the exhaust of the stuff that I burnt, and maybe some stuff unburnt, actually gets pushed out. All right, and then it draws in, begins drawing in the new mixture. Right, and it happens back and forth, so just let it run right now. Right, so it draws in the mixture, compresses it, ignites it, it pushes out the exhaust. And we can speed it up. Right, so this happens at a very high rate of speed. If you ever listen to your engine running, you can hear the click, 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 click of the valves opening and shutting as it runs. And you can see here how camshaft is used to help open and close those valves at the right time. All right, so that's what we're working with. This is a 4-stroke engine, as it says there on the web page. So let's go back to the presentation here. So a little bit of the terminology that we're going to be dealing with. Well, we have the overall stroke that the piston travels. So the piston goes all the way to the top to a point called top dead center. And top dead center is where the volume is at a minimum. So there's a clearance volume that exists. When the piston is all the way at the top, there's still a little bit of space at the top. So it's called the clearance volume. It's called, the location is called top dead center. All right, and that's the top of the stroke. And at the bottom of the stroke is bottom dead center. And that's where we have the maximum amount of volume that exists within the cylinder. The bore of our cylinder is essentially the diameter of the cylinder. Obviously, we've already talked about the piston, and we have some overall reciprocating motion as the piston goes up and down. And we've talked about the valves. And you could have a spark plug or a fuel injector, which we'll talk more with the diesel engines. But with ignition engines, spark ignition engines, you have a spark plug, and with diesel engines, you're going to have a fuel injector. All right, so let's look at some of these terms over here. R is the term typically used for the compression ratio, which is a very useful term, and we'll see it as we look at comparisons between spark ignition engines and compression ignition engines. But that the compression ratio is the volume, the max volume, max volume divided by the minimum volume. All right, if you remember what I just highlighted there, the max volume occurs at bottom dead center, so BDC, and the minimum volume occurs at top dead center. All right, so for spark ignition engine, this is typically lower. It's around 12. Obviously, it can vary depending on the engine. Whereas compression ignition engines, so they ignite via compression, they don't ignite using a spark plug. They range from 12 all the way up to 20 and maybe higher, again, depending on the engine, what's the setup. All right, so again, we'll get into more of that later, but there's some initial facts there for you. Displacement volume, so that's the volume at bottom dead center minus the volume at top dead center. So it's the overall volume displaced by the piston going from top dead center to bottom dead center, so all the way volume that exists in this space here. And finally, MEP, or the mean effective pressure. Mean effective pressure is the net work for one cycle divided by displacement volume, which we just calculated. Displacement V. All right, and mathematically we could say that's equal to our work net work. So net work, which we recommend for one cycle. Displacement volume is again our volume, bottom dead center minus the volume at top dead center. All right, so that'll be useful too as we look at some things as well. Another way we can look at this too is just rearranging and say, hey, what's the what's kind of a big W there? Let me erase that. Net work is equal to mean effective pressure times the quantity of the volume at bottom dead center minus the volume at top dead center. Right, so almost like this mean effective pressure is P dV, right? So you kind of see where that might come from. All right, so again, terms that might be useful later as we're doing get into calculations. All right, so that's kind of just your basic introduction to what overall is spark ignition engines, what they're about. Looking at the whole context of where these combustion engines work, it's a reciprocating internal combustion engine. Now we're going to look at other types of gas engines. So this is the first part of the gas engine chapter, and there's going to be a second part, but this is internal combustion engines. And so most gas turbines that we deal with are internal. There really aren't a whole lot of external, which may make sense. Specifically, what we looked at so far is spark ignition. All right, so it's a mixture of fuel and air, already pre-mixed, and that is ignited by a spark plug. All right, so this is relatively light, so you can see the value in having a more light engine, and it's lower in cost. All right, for compression ignition engines, we compress air to a very high pressure or temperature, and then it auto-ignites when we inject fuel into it. So if we go back here, right? So this is a spark plug or a fuel injector. So you can follow the 4-stroke process if you go back to the video, or you go to the video itself up here, which I'll put a link to that in the description. You'll see that you basically follow the same process, but instead of compressing the fuel-air mixture and igniting with a spark plug, you're going to compress air, and then the fuel injector is going to shoot fuel in little droplets into that air, and that's going to auto-ignite because of the high pressure and temperature. So that's what a compression ignition engine does. Now those engines, better fuel economy, so value there, and large amounts of power. So when we look at their applications, the spark ignition is used in automobiles, right? That's what you probably have in your car unless you're running a like Volkswagen as a popular turbo diesel, or if you have a hybrid or electric. Well, if you have a hybrid, you still have spark ignition. But anyway, so automobiles have the spark ignition, and advantages up to about 300 horsepower. So it's still valuable to have the spark ignition. But for higher levels of horsepower, for heavy trucks, ships, auxiliary power units, compression ignition is probably the way to go. So that's where we typically see their application. All right. You may be wondering, hey, what about a 2-stroke engine? So a 2-stroke engine you'll typically see in small, much smaller engines. It's much more compact. So you can think about gas-powered leaf blowers, gas-powered weed whackers, and especially 2-stroke engine small bike motorcycles. Again, mopeds, smaller motorcycles. But what we have here is if we go back to the 4-stroke engine, which I'm not going to now, but the 4-stroke engine, the piston is located within the cylinder, never goes below any ports that you see here or this one here. As a result, the oil that you pour into your engine, if you change, I hope you're changing your oil, stays down here and it lubricates everything down here in the crankcase in the bottom part. And some of it will get up here and burn a little bit, but typically it all stays down here. In the 2-stroke engine now, we have the fuel-air mixture coming in here, but you see how it's surrounding the crankcase? So the oil that we would normally add to the 4-stroke engine, we don't add in a separate port in a two-stroke engine. You actually add oil into the fuel-air mixture. You actually add some oil into your gas before you pour it into the tank of a two-stroke engine, or at least you should. If you don't, it'll seize up, and this has happened to me because I've done this. So you have this fuel-air mixture that sits around here below the piston. So when the piston comes down low enough, you can see it's about mid-stroke right now. When it comes down low enough, it's actually below the intake port. And so when it gets below there, the intake will shoot in the fuel-air mixture, and it'll fill this space. The piston will come back up, compress it, and the spark will ignite it, and it'll drive it back down. Now the problem with two-stroke engines, as you see, the intake port shoots in this nice fresh stuff, the fresh fuel-air mixture. And the exhaust port is going to be open at the exact same time as the intake port. So now you might have a lot of unburnt stuff going through all the way out the exhaust port, which is very much of a pollutant. And you're trying to burn this oil, which serves as a lubricant as well. So two-stroke engines, while light, relatively economical because of their lightness, are very pollution prone. So that's why they're not liked on a large basis. All right, so let's look at the piston-cylinder engine a little bit more in depth here. So again, a four-stroke engine process. There's an intake stroke. And during the intake stroke, when this valve is open, or I guess it depends on which valve is which, but if this one's where the fuel air mixture is coming in, at the intake stroke, it's the piston's going down at this point. And so during the intake, we're going from top dead center to bottom dead center. So the volume is increasing, and pressure decreases slightly and then increases because it's open to, in a way, it's open to atmosphere, but not really, but it's open to the gas entering. All right, so that's the intake stroke. Once the intake closes, once this valve over here closes, then we go into the compression stroke. So the piston now goes back up, and it compresses against these valves, that fuel air mixture that's now within the cylinder. So the compression happens, the volume goes down, as well as the pressure going up. All right. Then combustion is initiated. It's actually initiated before it gets to top dead center. We initiate on the way up because it takes a little bit, order of microseconds, for the combustion to get fully implemented. So we'll do it on the way up, so we get the full thrust of the power on the way down. All right. So when the combustion happens, combustion pressure goes up even higher, but now the volume starts to expand because the piston's going down as a result of the spark that happened right here. All right, so the power goes down. We open the exhaust. So this valve opens up, and then you go through the exhaust cycle here to push out the exhaust after the reaction. So those are the other strokes there. So the intake stroke, compression stroke, power stroke, when the expansion happens, so the driving after the combustion starts, and finally the exhaust stroke. All right. To look at it another way, right, so here's the same drawing here. We see pressure, top dead center, bottom dead center. So the compression stroke, we have the fuel air mixture that's already in here. So we're going to compress it upward. We're going to get the spark at the top that drives the piston downward. Combustion process is done. We're going to push up and get the exhaust out and then draw it in here for the intake stroke. Now I show you that again because what we're actually going to do to simplify this is the Otto cycle. And here's what happens with the Otto cycle. We're going to model, and let me start over here because this makes a little bit more sense let's start here. All right, so for the isentropic compression, we have we're compressing air. So this whole time we're not going to worry about the combustion process. We're not going to worry about mixture of fuel and air. It's just going to be straight air. So isentropic process, we're going to compress our air, and so we see with compression from state 1 to 2, from 1 to 2, it's isentropic compression. So the volume goes down and the pressure goes up. All right, now it's isentropic, so if we did a TS diagram, this would be a nice vertical line, but because this is a PV diagram, you'll see it obviously changes. So the pressure does go up during isentropic compression process. Kind of makes sense. Then we'll have constant volume heat addition. All right, so at the top, we're not going to change. Right, the piston is just going to stay there from states 2 to 3, so constant volume, and we're going to add some Q dot in. Right, so the Q dot in is going to come here from state 2 to 3. Then to model the exhaust stroke, we're going to have the piston come down. So we're going to have isentropic expansion. Right, so here's isentropic expansion, 3 to 4. Volume increases as we go down, and the pressure goes down as well. And then finally here, we're going to have constant volume heat rejection. So the piston's going to stay still, and we're just going to take heat out as that part. So the Q dot comes out here. So again, it's definitely a simplification. Looks more like a 2-stroke process than a 4-stroke process. But this is the model. The Otto cycle is the ideal Otto cycle is how we model our spark ignition engine. All right. So that's it for this presentation. The next presentation, I'll talk about the actual thermodynamic analysis, actual equations, and analysis of parameters. And I'll provide a link for that in the description as well.